Welcome to Lecture 3. Today we'll be looking at two more complicated examples of combinatorial proofs, but I wanted to start with a warm-up problem that you should be able to solve using the combinatorial techniques that we saw in the last lecture. The problem is simply to prove that n choose k is equal to n choose n minus k whenever n is at least k is at least 0. To do this, you'll need to look at an n-element set and find a bijection between its collection of subsets of size k and its collection of subsets of size n minus k. It's worth mentioning at this point that there's another name for expressions that look like n choose k. They're called binomial coefficients for reasons that we'll see later. I'll also mention that it's almost trivial to prove this identity using the formula we have for n choose k. However, this proof doesn't tell you as much as the bijective one. Now let's move on to a more interesting example. The notes talk about multisets, but for now I'm going to talk about socks. Here's a counting problem. Suppose I tell you that I have a sock drawer. There are 10 socks in the drawer, and every sock in the drawer is red, green, blue, or yellow. My question is, how many different sock drawers are possible? To solve this, our first step is of course to ask what we're actually counting. If we let n1 be the number of red socks, n2 be the number of green socks, and so on, then we can see that a sock drawer is the same thing as a 4-tuple of integers n1, n2, n3, n4, whose sum is equal to 10, where all of them are at least 0. As you can see, I've color-coded my algebra here, but none of what I'm doing actually needs the colors to make sense. Now we know what type of objects we're actually counting. Since we'd like to use a bijection, it now makes sense to put these objects we're counting into a set S. This definition just says that S is the set of 4 tuples of non-negative integers whose sum is equal to 10. For instance, S contains the element 0, 0, 10, 0, which corresponds to a sock drawer that's all blue socks, or 2, 3, 3, 2, which corresponds to a mixture. We want the size of S, and we're going to work this out by putting S into bijection with another set whose size is easier to find. It's not obvious what set to choose here, but here's the example that works. We're going to set T to be the set of all strings of length 13 that consist of 10 dots and 3 dividers. For example, here are two strings that belong to the set T. The first one goes divider, divider, then 10 dots, then a divider. The second one consists of 2 dots, a divider, 3 dots, another divider, 3 dots, another divider, and 2 more dots. I'm about to show you that S and T can be put into bijection. But before I tell you the bijection, I encourage you to pause and figure out what it should be. A hint is that the bijection will associate the two examples of elements of S on this slide with the two examples of elements of T on this slide. Here's my bijection F from S to T. F is going to send a 4-tuple n1, n2, n3, n4 that belongs to S, that is, 4 non-negative integers that add to 10, to a string consisting of n1 dots, then a divider, then n2 dots, then a divider, then n3 dots, then a divider, then n4 dots. Since the 4 n's always add to 10, this will always give you a string that consists of 10 dots and 3 dividers, that is, a string in T. Now we need the inverse of F. That is, we need to know how you would go from a string that belongs to the set T back to the 4-tuple in S which map to that string. By the way we defined F, the way you would work out the inverse of a string is to let n1 be the number of dots before the first divider, n2 be the number of dots between the first and second divider, and so on, and n4 is the number of dots after the last divider in the string. Both those definitions are on the abstract side, but if you apply them in individual examples, they shouldn't be too hard to understand. For instance, F of 4, 1, 1, 4 will be a string with 4 dots, a divider, a dot, a divider, a dot, a divider, and 4 dots. And you can do the same kind of thing in an example with G. So we've shown these sets are in bijection by giving a function between them and specifying the inverse of that function. It follows that the size of S, which is the number of possible sock drawers, is equal to the size of T, which is the number of length 13 strings that consist of 10 dots and 3 dividers. And the size of T is actually 13 choose 3. The reason for that is because I can describe a string in T by telling you the 3 positions where the dividers fall. Those 3 positions make a subset of the 13 possible positions of size 3 and each subset would give me a different string in T. We do have a formula for n choose k, and you can use the formula to show that 13 to choose 3 is 286, but it's fine to leave the answer in the n choose k form. Now let's stop talking about socks so we can sound more fancy. An n-element multiset with t types is defined to be a t-tuple n1, n2, up to nt of non-negative integers whose sum is equal to n. So for example, my sock drawer was a 10-element multiset with 4 types. The reason it's called a multiset is because it's like a set, but the elements can appear more than once. The n's keep track of how many times each element appears. If the n's were all 0 or 1, then this would essentially be a set. Here's a theorem about multisets. The number of n-element multisets with t types is equal to n plus t minus 1, choose t minus 1. Luckily, there's no need for us to prove this theorem because we've essentially already proved it. If you take my proof with sock drawers and you change all the 10s into n's and all the 4s into t's, then you'll find the same proof works. You end up with a bijection between the n-element multisets with t types and the strings consisting of n dots and t minus 1 dividers. When teaching this course, there are some common questions I get from students about proofs like this. The first is whether I'm being mathematically rigorous in giving a proof this way, and the answer is yes, I am. You might be used to proofs looking more like computations, or even believe a proof needs to be a computation to be rigorous. This is not true. I wanted to compute the size of a set S, so I put S into bijection with another set T, and computed the size of T, and therefore the size of S. All the ideas were logically rigorous, including the way I specified the function. In general, as mathematics gets more advanced and interesting, it relies less on computations and more on logical arguments made in plain English. The second question is a harder one to answer. How do I come up with proofs like this? In the example we just looked at, you might ask why T was the right set to consider, and indeed what strings of dots and dividers have to do with multisets. The answer is that there is no general method. Coming up with a combinatorial proof requires some creativity. It requires an idea. It will be easier to have good ideas with more practice. Often ideas that work in one proof can be applied to another. In some sense, it's no different than learning a musical instrument or getting good at a video game. Although, of course, math is more fun than both those things. Here's another example of an identity we can prove combinatorially. This time we'll use double counting rather than a bijection. We're going to prove that n choose k plus 1 is the same as the sum of m choose k over all m between k and n minus 1. Before I write down the proof, I'll talk about how we might go about finding it. As always with a combinatorial proof, we're interested in the meaning of the terms on either side of the identity. Here, this is easier on the right-hand side. Of course, n choose k plus 1 is the same as the number of k plus 1 element subsets of the set of integers from 1 up to n. Let's call the set of all such subsets S. So the size of S is the right-hand side of the identity. The left-hand side is the sum of a number of different terms. So one way to prove that the left-hand side is equal to the right-hand side is to write the set S as the union of a collection of disjoint subsets so that the sizes of those subsets are m choose k, m plus 1 choose k, and so on. So we want a combinatorial meaning for the terms on the left that also relates to the set S. It's not immediately clear what to do here, since the terms on the left seem to relate to k-element subsets, not k plus 1 element subsets. However, we can do something to relate those two notions. M choose k is of course the number of k-element subsets of 1 up to m. And that is the same as the number of k plus 1 element subsets of 1 up to n, whose maximum is equal to m plus 1. This is because we can describe a k plus 1 element subset of 1 up to n, whose maximum is m plus 1, simply by telling you its k other elements, all of which are somewhere between 1 and m. That was just rough work, but hopefully it gives an idea of how we can actually write down a proof. To prove this identity, we'll let S be the collection of all k plus 1 element subsets of 1 up to n, and then we split S up according to the maximum element of its members. For each m between k and n minus 1, we'll let S sub m be the set of all sets in S whose maximum is equal to m plus 1. Clearly, the maximum of any set in S is somewhere between k plus 1 and n, and it follows that S is the disjoint union of the sets sk, sk plus 1, and so on up to Sn minus 1. As we saw on the previous slide, we also have that the size of S sub m is equal to m choose k for each m. These ideas all turn the proof into a one-line computation. The right-hand side, n choose k plus 1, is equal to the size of S. Because S is the disjoint union of the Sm, the size of S is the sum of the sizes of the Sm. And finally, the size of each Sm is equal to m choose k, as we've just argued. Together this gives a proof. This identity has an informal name which is kind of cute. It's called the hockey stick identity. This is because it says that if I follow a path in Pascal's triangle from the upper right hand side down diagonally to the left as shown, and I add the numbers I get along my path, then the sum I get is 1 down and to the right of the end of my path. I hope you enjoyed the first week of lectures. Next week we'll see where the algebra starts coming in.